Welcome to the second part of the lecture of October 21st. This part deals with an application of the codes which we have developed for neural networks to solve differential equations. Now, this is a very, very active research field, and you will find many different research articles on the implementation of neural networks and solving differential equations, whether these are ordinary differential equations or partial differential equations. A field which is extremely important nowadays is a field which has been dubbed physics-informed neural networks. You can find a recent overview article here on scientific machine learning for physics-informed neural networks, where we are and what's next. And there are textbooks on the introduction of neural methods to solving differential equations, and many other research possibilities which have popped up in the last years. So this is a very, very active field of research. And for those of you who are studying differential equations, we are proposing a path in project number 3, which deals with the implementation of neural networks in solving the diffusion equation. And you will see an example below here on how you can actually solve the diffusion equation in, for example, one dimension plus a spatial dimension. Now, before we move on, we are going to dive back into the whiteboard and remind ourselves about some famous differential equations. So let us start with a differential equation which many of you probably have seen many times. And it's actually one of the first ones which we encounter in a course where we solve differential equations. And one of these is the differential equation for exponential decay. And that equation is given by the derivative of a function g, where g is the function we want to find, with respect to a variable x. So x could be time, or it could be any other variable. So let's just call it x. And in this specific case, we have a constant gamma, and we have a g of x here. And this is a famous differential equation whose solution we know. So x would typically be now defined from 0 to infinity, could be, or we could put a finite limit to it. And the solution to this differential equation is given by g of x equal to some constant, which we are going to label as a g0. And then we have the exponential of minus gamma. And this gamma is normally called the exponential decay parameter, or the half-life parameter, if you're dealing with exponential decays as a physical process. And this g0 is simply given by the initial condition, where we have x equal to 0 here. So this equation is something which many of you have encountered and seen several times. Let us now also look at another famous differential equation, and that's an equation which is similar to this one, and that's the equation for population growth. And this is another equation which we're going to encounter in the examples in the Jupyter Notebook here. So the equation for population growth, let's just write it down here. And now we replace x with time, t. So we have a derivative of dg dt, and that's given by some constant alpha, which is normally larger than 0. And this is multiplied with g of t. And then we have another constant, a minus g of t. And gt is the population density at a given time. The parameter alpha is assumed to be larger than 0. And then we have something which we call the growth rate, which is this parameter a. And this is also assumed to be larger than 0. And the max population, so this a0 represents then the max population. So alpha is the growth rate, and a larger than 0 is the max population here. Now, the population at t equals 0 is something which we again are going to label as this g0. And this equation has an analytical solution as well. So the analytical solution, and some of you may have encountered this equation already. So let's write it down, because in the programs, which follow pretty soon, we are going to compare the solution with a neural network with the analytical solution. So this analytical solution is given by a g of t. We have a numerator, a times g0, the initial condition, and this is divided by g0 plus a minus g0, and this is multiplied with the exponential of minus alpha times a times t. Now, if we study an equations more carefully, the typical way by which we would rewrite these equations is in terms of a function which we want to drive to zero. So let's take a closer look at the exponential decay. And the same approach applies to the population growth or to any differential equation, which we are going to discuss in the coming. So this equation here is an equation where we can rewrite and just shift the right-hand side over to the left-hand side, and we would have a minus, and then have a minus of gamma times g of x equal to 0. This defines a function which is now a function of x. You can see that this is also a function of g of x, and it is a function of the derivative of g. And we want this function to be equal to 0. Now, we can generalize this to a function which now contains higher order derivatives. So these equations which we're looking at now are equations which we call first order equation, because we have the derivative of the function we want to find to first order. And if we want to look at the second derivative, then we will have a second order equation. And if we have a third derivative, then we have a third order equation, etc., etc. So in general, what we would have is a function f, which now is defined by the variable x. This is a one-dimensional equation. We have g of x, we have the first derivative, we have the second derivative, and this goes all the way up to the nth derivative as a function of x here. And we are driving this one to zeros. Now, in this specific case, for exponential decay, we have only the first derivative, but there's nothing which now hinders us to include higher and higher derivatives. And you will see examples of this below here, where we're also going to encounter another type of differential equation. And that equation is a two-point boundary value problem. And later, we are going to extend all this machinery to partial differential equations, which means we have more than one variable. A typical equation which we are going to encounter down in the slides here is a diffusion equation in one dimension plus time. We are going to look at the wave equation in one dimension plus time, but all these equations can be extended to higher order dimensionalities. Now, one of the things and one of the reasons why neural networks have become so popular in solving these type of equations is that many of these equations are high dimensional ones. If we are studying turbulence in, let's say, weather forecasting, we need often a very, very fine grid in order to be able to simulate properly the Navier-Stokes equations. And a very, very fine resolution of the grid means also that we have a higher dimensionality in the number of integration points. And this makes it much more difficult to use standard methods. And this is one of the reasons why neural networks have become so popular. Now, we are going to see several examples of this. Before we move, however, let's remind ourselves quickly about some of the traditional methods for solving differential equations. So if you look at these equations which we have here, these simple first-order equations, the standard approach to solving these equations numerically, if we don't have an analytical solution, which is often the case, is to perform Taylor expansions. And Taylor expansion are the functions which we want to find the solution of are essentially the standard recipe, and they lead to a scheme which is normally called a finite difference scheme, where we would discretize time or the variable x or the variable under study. So let's take a closer look at the basic standard schemes which you may have encountered earlier. And these are normally called finite difference schemes. And you will find this material in the Jupyter notebook as well. And these schemes are all simple or more complicated manipulations of Taylor expansions. So let's now look at a Taylor expansion of a function g, which depends on time. So we have a function g, and we are going to make an expansion around the time t plus delta t. And we know very well that this is just given by the function at the value t. We have a delta t multiplied with the first derivative, dg dt, evaluated at this time t. We have the second derivative. We have a delta t squared. So delta t is a small step which we are making, 2 factorial. And then we have the second derivative, dg dt, evaluated at t. And then we have the higher order terms, which go like delta t to the power of 3 or higher. Now, what's pretty common now is that we discretize time. So time here in this specific case can be seen as a continuous variable. So we are going to discretize. So t becomes a discrete variable, t of I, and it's going to have a recipe where we set t of I is given now by some t0, the initial time, plus I times delta t. And if we have n plus 1 integration points, as we call them, or mesh points, the I variable runs from 0, 1, 2, up to some variable n. And you see now that the variable t of n, which is the end point, corresponds then to t0 plus n times delta t, which means again that delta t is defined in terms of the final time minus the initial time divided by the number of integration points, which is actually n plus 1, since we start with 0. So when I is 0, then we simply have t0, as expected. So this leads to a discretization of the domain of integration. It means also that our variables g of t plus delta t, and in principle now, since we are solving a different problem by discretizing, we should use another symbol for g, but we are going to stay with the same symbol. So this becomes a g of t of I plus delta t, and we are going to use an acronym here, a subscript, where we have a g of I plus 1. So just one step. And if we just go back one step, so t of I minus delta t, we would have a subscript of I minus 1. So if we now look at the equation which we Taylor expanded, we would now have the following recipe. We would have a g of I plus 1, which is equal, and now we are going to simply stop at the first derivative. And that gives us g of I plus a delta t multiplied with g of I derivative. So when it says this with a subscript I, it means that this is evaluated at time t of I. So just a quick reminder, when we look at dg dt at t equal to t of I, this is simply this quantity g of I derivative. So with the discretization now, we have a recipe for calculating this g of I plus 1. So we would typically start with I equals 0. And we know in general is dg dt. So quite often we have an expression for dg dt. And in the exponential decay case, this was simply given by minus gamma of g of t, where we now have replaced x with time. And if we now look at the equation which we have, it means that this g of 1 when we start with I equals 0, is now approximated with G0 minus, and then we have a gamma, and then we have a G0 here, where we simply plugged in the equation for minus gamma of G at t equals 0. And that is the same as minus gamma of G0. And we see now that this equation is something which we can keep integrating to the final point. So we would have a G of 2, which depends on the previous variable, and that is a G of 1 minus gamma of G of 1. And this would continue till the final endpoint, till G of n. And then we have integrated up, and we have hopefully found a decent solution to the problem. So this would be n, and then we would have n minus 1 minus gamma of G of n minus 1. And this is the same recipe now, which we would use for other types of differential equations. We can become a little bit more ambitious, and we could think of replacing the Taylor expansion, which we did here and where we stopped at first order. We could now replace this with higher order equations. Now, this equation here, where we move forward with a step size, delta t, and a truncation at the first derivative, is called Euler's method. And this is typically referred to as the Euler formula for calculating the derivatives, or the Euler formula for integrating a differential equation to first order. So this is the simplest possible approach which we can take. Now, another equation which we are going to meet a little bit later here is a 2-point boundary value problem. So let's take a look at that one. So this equation here is something which would apply to the population growth as well. And these equations here, they have an error which goes like delta t squared, because we made a truncation at the order of the first derivative. And then the terms which we're leaving out run like delta t squared or higher derivative, or delta t cubed, which we have higher derivatives. Now, another equation which we are also going to look at is a 2-point boundary value problem. And here we have a famous equation, which is called the Poisson equation. And we're going to look at the Poisson equation in 1 dimension. We can extend this easily to 2 or 3 dimensions, but let's stay with the 1-dimensional Poisson equation, which is an equation which now depends on the second derivative and some function f of x. So let's look at the 2-point boundary value problem. And this is normally a problem which is solved using linear algebra methods. And some of you may have encountered this if you took a course in numerical mathematics or numerical physics. So we are going to have a function now, minus g, which is the second derivative, and this is the unknown function, which we want to find the solution to. And this is given by some function f of x, where this is a known function. And in this specific case, we can now define x to live between 0 and 1. And since this is a 2-point boundary value problem, what we are saying now is that g of x equals 0 is equal to g of x equal to 1, the 2 endpoints, and we just put the solution to 0. So this is normally called a Dirichlet boundary condition when we have constant values at the endpoints. And you may have encountered this when you studied the solution of differential equations. If we have the derivative, for instance, then these change the name to Neumann or Neumann boundary conditions. So this is a 2-point boundary problem, and we are going to assume now that this function f of x is known, which is the typical case. So f of x, we are going to give that one in terms of 3x. This is the equation which we are going to study down in the lecture notes. And this, with this f of x, we have an analytical solution for the problem, x or 1 minus x multiplied with the exponential of x. So how do we solve this problem? Now we have a second derivative. And there is a famous formula for the second derivative. This famous formula is an approximation now, but let's now write it without an approximation. And this contains it's actually given by a manipulation of two Taylor expansions. One Taylor expansion where we take x plus delta x, and one where we take x minus delta x. And then we simply add these two Taylor expansions, which means that we get rid of the odd derivatives. This formula here is now given without any approximation by g of delta x. So we have made a Taylor expansion around x plus delta x and x minus delta x minus 2 times g of x divided by the step size which we are making plus higher order terms. And these higher order terms go like delta x cubed or higher. Actually, they appear as delta x to the power of 4 because when we manipulate these two Taylor expansion, we get rid of all the odd terms. So in principle, this one should actually go like delta x to the power of 4. So this is the error which we are going to make. Actually, what we have done, and this is not the full truth, we have divided by delta x squared. So that means that the second derivative is now isolated. So we have delta x squared in the denominator, which means that the fourth derivative which appears has delta x to the power of 4 divided by delta x to the power of 2, which then again means that the error which we make, truncation, goes like delta x squared. But in principle, we truncated this expansion at the order of delta x to the power of 4. And these terms which you see here are normally what define the error in the approximation. So when we are setting up the equations, we are now going to make an approximation, obviously, because we don't want to involve higher derivatives. So we are simply going to say now that this becomes minus, and this is a g of x plus delta x plus g of x minus delta x. So this is the differential equation we are looking at of g of x divided by delta x squared. And this is equal to this function f of x. Now, when we discretize then, we are going to change x to some x of I, and this x of I is going to be given again by x0 plus I times some step size delta x. And the step size takes the same expression. If I goes from 0, 1 up to n, then delta x is simply x of n, the endpoint, minus x0 divided by the number of integration points. Keep in mind that the number of integration points runs from 0 up to n, so we have n plus 1 points. Now, if xn is 1 and x0 is 0, then this is simply 1 divided by n. But we're just going to leave them unspecified. Now, the next case is that we have minus this g of I, second derivative, which is now simply minus d second derivative of g of d of x, evaluate at x equal to x of I. And we are then going to replace the x plus delta x with an x of I plus delta x. So we end up with an equation now, which looks like this. So we have a g of I, second derivative, and we are taking away the approximation sign now. So we're just putting an equality sign. So we get a g of I minus g of I plus 1. And we have a minus g of I minus 1. And then we have plus 2 g of I divided by delta x squared. And this is equal to a discretized variant of f of I as well. This is something which we then can rewrite in terms of a matrix times a vector, the unknown vector g, and that is equal to another vector f. So you would often see this rewritten in terms of a matrix A times an unknown vector g, and that is equal to some vector f multiplied with delta x squared. And this G is now simply going to contain the unknown points because we know the endpoints. So we would have a G1, a G2, up to a G of n minus 1. These are the unknown points because we know the endpoints. So G0 and Gn have been fixed to be 0. And the matrix A, it shouldn't come as a surprise that this is given by a tridiagonal matrix. So we will have 2 along the diagonals. And then we have the, above the diagonal, there's a minus 1, which then come from these expressions here and this expression here. So that means that we have minus 1s, etc., all the way down here. So this is a tridiagonal matrix, and the vector f contains simply the known function f. This equation here is normally solved by standard linear algebra problems with Gaussian elimination. You don't need to invert a matrix because you have a much more efficient algorithm, which is called the Thomas algorithm. But these are some of the basic recipes which we are going to encounter when we want to compare our neural network solution with the standard ordinary differential equation schemes, or alternatively, if we are lucky, we have analytical solutions. Now, what is the basic recipe which we are going to implement with neural networks? So let's now look at neural networks and the basic recipe which we want to implement. So we are going to make an ansatz for the solution. So keep in mind also that we defined a function f, which is different from the one we had in the previous case for the 2-point boundary problem. So we have a function x now which depends on the unknown function. And this is a function of all the derivatives which are involved in the problem. So we have just subtracted the right-hand side from the left-hand side, and we want this to be 0. Now, when we now plug in a neural network, we need to make an ansatz for the problem. So we are going to make an ansatz. So we have a trial solution. And this trial solution is given by a g of t as a function of x. We are now still looking at the one-dimensional problems. And we are going to have 2 functions, one h1, which then satisfies the boundary conditions or initial conditions. Initial and or, if we now have a partial differential equation, we also need to think of boundary conditions. Plus a function h2 here, which is now given by this input x, which we have, and a neural network. So this neural network now is labeled as an n, takes x as an input, and then it has a set of parameters theta, which we need to define. So if we think of the exponential decay as a simple example here, what we could do then is simply to say that this g of t of x is given by g0, so that we obey the boundary condition, plus an x times a neural network. So this function h2 could simply be us setting up the neural network here. And you see now that when x is equal to 0, in this specific case which you see here, when x is 0, then this term is 0, and the solution is simply given by g0. So in this particular case, this function h of 1 is now given by the constant g0, which defines initial conditions. If we look at the 2-point boundary value problem, so let's take a look at that one and how we could set up a trial wave function. So let's take that 2-point boundary value problem, the population growth case is pretty similar to the exponential decay case. So let's look at the 2-point boundary value problem. So in that particular case, we could now set up a function g of t of x, which we could define as, so this is one of many possibilities, x of -1 times x multiplied with a neural network with parameters theta to be defined. And what we have here is that if x is equal to 0, then we see that g of t of 0 is equal to 0, which was one of the boundary conditions. If I put x equal to 1, you also see that g of t of 1 is equal to 0. So this is a very simple way by which we can fulfill the boundary conditions. Now, what is the basic recipe when we now are setting up a neural network here? Now, what we are going to do now is to define a cost function or loss function. And a very natural one to set up is a c of x of theta. So theta are the parameters. And we have a given number of integration points. And the sum runs from I equals 0 up to n minus 1. And now we have this function which we want to drive to 0. So we have an x of I, we have a g of x of I, and this is going to be a function of these parameters, of this trial function. And so it will depend on the parameters theta, but we're going to hide the parameters theta in these functions here. So this will have higher derivatives depending on the type of differential equation we have. And this goes all the way up to a g of n, not of n, but I should put an m here to distinguish it from the number of points which we are having. So n is now the order of the differential equation. And this is calculated at point I. And now we square it. So what we are doing here is that we are simply squaring the difference between the right-hand side and the left-hand side. So what this means is that we are going to have a function, if we now add the parameters theta, we are going to find the optimal parameters theta. So this is theta optimal with a hat, as we have normally used these equations, of 1 over n. And then I have a sum over all these variables, and I have my x of I have my gt of x of I of theta, and this continues with all the higher derivatives. So this is a function f here. Sorry, let me just quickly, because I'm running a little bit out of space here. So what we are going to do now is to optimize this function here of sum over I. So we have the function f, and this function is a function of x of I, and then I have my gt, and this is a function of x of I and theta. I have the higher derivatives, gt, x of I of theta, and this goes all the way up to the nth derivative of t of x of I of theta, and this is squared. So if I look at exponential decay, a simple example, which is the first example we're going to meet now. In that case, my cost function, x of theta, is equal to 1 divided by n, and I sum over all the points which I'm setting up, and I'm having my function g of t prime, which is a derivative of x of I of theta. So the parameters theta are unknown, and we are going to train them by setting up a neural network. And this is a minus. And now we're putting in the expression for the derivative, which is minus gamma of g of t of x of I of theta. And this equation here, this difference, is then squared. So that's the equation which we now are going to implement in our first numerical application of neural networks to the solution of differential equations. So what we're going to do now is to have a cost function which looks almost like a mean squared error. So we are squaring the difference. We could have taken the absolute value, if we want to, of the difference between g derivative and the right-hand side of the differential equation, but we are going to square it because that will also amplify the differences. And then we are going to set up an iterative scheme with the feed-forward propagation and the back propagation as well. And with a given number of iteration, the hope then is that the difference between the left-hand side and the right-hand side, which is now encoded in this cost function, it goes slowly and slowly to zero. So let's turn back to the Jupyter notebook and have a look at how we can implement this using the codes which we have developed for differential equations and neural networks. We are now back to the Jupyter notebook. The notes which you see here were developed by Christina Hein when she was a teaching assistant at this course. She's now wrapping up her PhD at the Department of Computer Science. So the ordinary differential equation which we looked at before when we were discussing things on the whiteboard is something which we can write in a general form like this function f, which is a difference between the right-hand side and the left-hand side, and we want to drive this difference to zero. And this is basically the approach which we are going to take in the solution of the differential equation. And the approach then is to write the trial solution in terms of some function h1, which reflects the boundary conditions or the initial conditions for both, and a function h2 now, which is a function of a neural network. And the case which we are going to start with, when we have set up the minimization problem, so this is so p here is now the same as the theta, which we had in these slides. We have n data points, which are given here. And then we are simply going to drive this difference between the left-hand side and the right-hand side of the differential equation squared. And we're going to drive this to zero. That's the basic recipe. And we are going to optimize the parameters by calculating the derivative of this function here. And that's going to define the gradients when we use automatic differentiation. So the codes which we have developed before for neural networks are codes which we now can utilize fully here. And as I mentioned in the beginning, for project number 2, there is a path which is tailored to those of you who have been studying differential equations, whether these are finite element methods or finite difference or both. And if you want to practice and study the solution of the same equations with neural networks, that would be an excellent approach where you can actually reuse everything you did in project number 2. So we are going to minimize this function using gradient descent, obviously, and the gradient descent equations are coming from the back propagation algorithm with a chain rule and automatic differentiation, which makes life much, much easier because it's much easier to replace the different functions f here with the inputs like g, the second derivative, first derivatives, etc., etc. It's much easier to make a neural network code with automatic differentiation because that gives a lot of flexibility in setting up the derivatives. And the first example is the one which we discussed at the very beginning on the whiteboard notes, and that's just the standard exponential decay. And the function we want to find is actually the solution to this problem. We know the analytical solution. This is essentially the same thing which we did before. And we are putting in parameters, just 2 chosen parameters, gamma equal 2, and we put g0 equal to 10. And then the trial function is now given by the function h1, which respects the boundary conditions, and then we have this function h2 here. And the way we did it was simply to have h1 equal to this parameter g0, the initial condition, and then we multiplied x with a neural network. Now, when we are setting up the network, we need to specify the number of hidden layers. So below you will find a flexible code, which then simply implements back propagation, updates the gradients, and the gradients are calculated using automatic differentiation. And as you can see here, the function which we are setting up as a trial function is simply this G0 plus X times R. And this is the one we want to set up. We are optimizing this problem here, which was also discussed previously. And if we have one hidden layer, we need this as a function of the parameters of the hidden layer and as a parameters of the output layer. So if we have a given number of nodes and a given number of input variables and a given number of output variables, then we know exactly what the dimensionalities are of the hidden weights, the output weights, the hidden biases, and the output biases. This is as before. So the codes which you have developed for project number 2 are codes which you can now use directly to solve these differential equations. So when we do this, this is essentially what we end up doing. So we are going to skip these technicalities here because this is essentially us setting up a neural network as before, with the number of hidden variables, the hidden biases, the hidden weights, multiplied with the inputs, which is a vector now which contains the different input variables from x0 to xn. We have all the hidden variables. And this is the first function, which is the input to the activation function, the z, to a given node I. And then we know that we can choose different activation functions. And in this specific case, the activation function is just a plain sigmoid function, as we've been discussing before. And then we continue. We have the output layer, which now contains the weights of the output. It contains the output from the hidden layer, which I just labeled as an X here. And then we have the final technicalities with the output, which we normally, when we have a regression type of problem, this is not a classification problem, then the output is simply the output from the output nodes without being modulated by an activation function. And this is essentially us setting up the same matrices or vectors as we did in the setup of our neural network code. And in the back propagation, we are finding the derivatives of this function here. And that means that we get the different gradients and we have the update of the hidden parameters and the update of the output parameters. And this is just as before. So the code here is actually pretty straightforward and simple. So you see I have a sigmoid here. I'm setting up the hidden weights and the hidden outputs. I'm setting up their biases a little bit down here. I am reshaping my number of the X here, which is now given by the number of input values. And I assume that the input layer does nothing to the input. And I'm now add a row of ones to include the bias. I'm setting up the hidden input to the sigmoid function. I'm finding the hidden output, which is now given by the sigmoid function here, which takes as input that. This is just as before. I include the bias. I'm producing the output here, and the output is simply given by the matrix multiplication or matrix vector multiplications, depending on the dimensionalities which we have. And this outputs my return here. And I'm obviously having so this sets up simply the network. And then below here, I'm actually setting up the back propagation algorithm with all the gradients which need to be evaluated. So my trial wave function is simply given now by the initial condition, which I put to 10. And then I have X times my neural network with the parameters. And my right side of the ordinary differential equation is simply this parameter gamma times this trial wave function. My cost function is simply now, if we now look at the expression here, it's simply now given by the derivative, which I calculate here by using automatic differentiation. So just keep that in mind. So I take the gradients here, and then I simply subtract the function and I square the result. And this is my cost function. And that is something which I now divide by the number of data points which I have. So this is my cost function, which I return here. And here I'm setting up the neural network. I am implementing the gradient descent. I have the gradients, and I'm simply updating the parameters. This is as simply as we can put the neural network calculation here. Now, pay attention here that there is no fancy way of setting up the gradients. So we have a learning rate which has been fixed, and we are running learning with a learning rate of 10 to the minus 3, which I call lambda here. The number of iterations is 10,000. So this is not a very advanced calculation in the sense that we are not updating the learning rates in any intelligent way. This is just a plain brute force gradient descent. So you see that there's a lot of room for improvements here. And I'm just running with 10 hidden neurons. And then I simply call my solution to the neural network, and I compare finally with the exact solution. This is as simply as you can do it. And you see now that the initial cost function with the guess which we had is pretty bad. So this is 367. But after these 10,000 iterations, which are quite many, I'm now getting a final cost function which is on the order of 10 to the minus 2. And the max absolute difference is also on the order of 10 minus 2. So with 10,000 iterations and only 10 hidden nodes, I'm actually getting a result which is pretty decent. So this is a comparison between the analytical solution and the numerical solution, as you can see here. Now, we can get more ambitious, and we can improve this by adding more hidden layers. So in this case here, I'm now simply adding 2 hidden layers, as you can see down here. So this is exactly the same code. You will see the same cost function. We are using gradient descent to calculate the derivatives. Sorry. We are using automatic differentiation to calculate the derivatives, which is something I would highly recommend if you're writing a similar code yourself. And then in this particular case, I'm now increasing the number of hidden layers to 2. So if I rerun these calculations, you can then see that again, in the first case, we have a cost function, which is, it's not optimal. 324 is the difference between the right-hand side and the left-hand side. It's going to take a little bit more time. But in this particular case, with 10,000 iterations and the same learning rate, we're actually getting a result which was worse than the previous case. So it seems that one hidden layer is doing a pretty good job. Now we can change the learning rate here and just rerun the calculations and just see what happens. So the first error is the same, and you will see that there is obviously a sensitivity to the value of the learning rate. So here the learning rate is pretty small. And in this particular case, we are getting, in the previous case, we had 0.1, and now we are getting 10 to the minus 3. And essentially what we have after this number of iterations is a result which is practically almost the same as the analytical result. So you see this application which we have here, where we calculate the derivatives. So this is just the update of the gradients. And we have a lambda parameter here, which is set to 0.01 when we had 10 to the minus 3. This gave us a poorer result. So we would need to play around with different types of different values for the learning rate. And clearly we would have to improve the update of the learning rate with some of these optimizers like Adam. We would use stochastic gradient descent, etc., etc. All the details, the fine details, which we have been adding to our neural network project. So this is just us demonstrating how you can calculate or solve a differential equation using deep learning methods like neural networks. Now, what follows next here is the population growth equation, which you were introduced to before the break. And we are going to do exactly the same setup. We are going to have a similar trial function now. We have replaced x with t, time. We have an analytical solution we are going to compare with. And then we can use the same function using autograd to calculate derivatives. So here, the only thing which we have done is to change the cost function. Or rather, what we have done, we've kept the cost function, but we have changed the function which we want to evaluate. And in this specific case, the only thing which changes from the previous code are the set of parameters we're having, because now we have one more parameter, this parameter A, which is the total population, the max population. And then we have this growth parameter alpha. And if we now rerun these codes, we would see something similar. And in this specific case, we actually get a better initial cost by accident. We can change the learning rate. So here we have got an error which is on the order of 10 to the minus 4. So if we now change the learning rate here, and we have only 1,000 iterations, and in this particular case, I'm having two hidden layers, one with 100 neurons, so I'm actually increasing the number of neurons. In the previous case, I had only 10. Now, since my equation is a little bit more complicated, I'm putting in 100 neurons and 50, so it's still pretty fast. So now just keep in mind this number here, 10 to the minus, it's a 4 times 10 to the minus 4. So let's see how this changes when we change the learning rate. And now you see actually with this learning rate, the error has increased. Whereas in the previous case, when we had 10 to the minus 3, we actually got a better result than the one with 10 to the minus 3. And you see also that the max absolute difference is on the order of 10 to the minus 4, 10 to the minus 3rd, sorry. And again, there's a very small difference between the analytical result and the neural network. Now we can also, since we have gotten a little bit more ambitious, we could try to compare the solution of this differential equation using Euler's method. Now, this is, as I should say, is an unfair comparison, because solving this type of equations, you would not use Euler's method. You would use some higher order methods like Runge-Kutta to second order, or even a better one, which would be Runge-Kutta to fourth order. This is also a case of equation where we are not conserving quantities like energies. So that means that the Runge-Kutta solver would actually be much, much better. So when you're making the comparison here with Euler's method, this is essentially what we covered on the whiteboard. So we can now simply compare our results from the neural network calculation with a standard Euler solver. And you can see now that the max absolute difference between Euler method and analytical result is 0.01. But this is simply because we are doing something unfair. The error goes like delta t squared. We are also having few integration points. And many of these methods do behave better if we give more integration points. And you will see now that the number of integration points is just 10, which is a very unfair comparison with a neural network calculation. So if we were to increase this one to 100, we would actually get a better result for Euler's method. So this is going to take a little bit more time, because now we have suddenly 100 points, which also enters the calculation of the neural network. So this will quickly take more time. The more points we want to evaluate, the more evaluations we need to do now. And then you see suddenly, so the final cost is actually pretty small. It's 3 times 10 to the minus 4th. So we see that the Euler method now, when we increase the number of points, is doing better than the neural network. So the wisdom you can extract from many of these simpler calculations is that the neural network is not going to perform equally well as the standard finite difference of finite element methods when you are dealing with low dimensional types of problems. So here, as I said in the previous example which we run, it was an unfair comparison. When we increase the number of integration points, you see now that the difference between the analytical solution and Euler's method is shrinking, whereas the neural network stays more or less at the same value as we had before. So if I now want to change things here, I would have to rethink and train the number of the values for the learning rates. I could now also look at the different number of parameters defining the neural network. I could increase the number of iterations, etc. So if I rerun this case here, but still with 100 points, the initial cost is still 0.186. But then I can now try to set up a different I'm trying a different learning rate. And in this specific case, you see that this learning rate is actually bringing me to a higher value. So Euler's method stays the same. So if you're dealing with high dimensional differential equation, this is often where the neural network calculation will outperform the standard finite element or finite difference solvers. The next case, which we looked at the whiteboard, was this one-dimensional Poisson equation, which is given by this second-order differential equation. And this is a typical problem which we would solve by linear algebra problems. And if I use AutoGrad here, if I just rerun it, you see now so this is just the same type of equations. The only thing is that we are now having a different trial network, which is given by, this is the analytical solution. So I'm putting in a trial which goes like x, so 1 minus x, and this gives me the boundary conditions. So when x is 0, I get 0. When x is 1, I get 0. So that's a way by which I can now implement the boundary conditions. And if I do this and run the code again, the only difference is the type of functions which I'm plugging in. That's the only difference from the previous code. So you see now I have this function f of x, which I need to define for the specific case. I need to define the trial function here. That's, again, the only difference. And that trial function gives a new cost function, but I can keep my cost function the same as before. There is no need to change that. That's just a difference between the left-hand side and the right-hand side, except that now I have a second derivative, which I need to plug in. But essentially what I have is more or less the same type of equation. So in this case, with 10 integration points, I see that they have an absolute difference, which is pretty small. This is the difference between my analytical result and the neural network, which means that with these 10 integration points, I'm actually getting a result which is pretty good. I can now use my standard finite difference scheme based on the Taylor expansions, which we discussed earlier. And then I can run a comparison with the solution of the differential equations by solving this linear algebra problem. So I have the analytical solutions I can compare with, but then I can also use the standard linear algebra solver, which is given by an algorithm based on Gaussian elimination, which is called Thomas algorithm. And that, since the matrix is a tri-diagonal matrix, Thomas's algorithm is a very efficient algorithm, which gives us roughly, if we have a matrix of dimensionality n times n, it gives us roughly between 4 times n to 8 times n floating point operations. If I were just to do a plain matrix inversion here, that would give me n cubed floating point operations. So Thomas' algorithm is the one you would use when you have a matrix which is tri-diagonal. And in particular, if you have constant elements along the diagonal and constant elements above and below the diagonal. So when you now are setting up the code here, we can then rerun it and compare. So the neural network code is essentially the same as we did with the exponential decay, except that now we have a slightly different trial function which respects the boundary conditions. And if I run it, you see now that I'm plotting the difference between the solution with the numerical scheme. So my neural network using AutoGrad gives actually a very small difference. So I have a difference which is 4 to 10 to the minus 4th. And the difference between the analytical solution and the numerical scheme based on the linear algebra algorithm, the Thomas algorithm, is now giving me roughly 1 order magnitude higher error. However, this is again an unfair comparison because I took only 10 integration points. So if I increase the number of integration points, then I will get something which then is going to give me a better result. So I could now increase this to 100. And just keep in mind the result which we had with the neural network, which is 4 times 10 to the minus 4. So let's see what happens if we now increase to 100 integration points. So one of the things you will often notice is that the error which you get with a neural network doesn't change that much as a function of the number of integration points. However, the linear algebra solver, which we have adopted, the Thomas algorithm, gets better and better when we now increase the number of integration points. And that is simply because the error which we make is given by delta x to some power. So in the previous case, when we had a domain from 0 to 1 and 10 points, then delta x is 1 divided by 10. When we have 100 integration points, then delta x is 1 divided by 100. And this is squared. So that means we have an error of 10 to the minus 4, which means, again, as you can see here, that the difference between the numerical scheme and the analytical solution is suddenly 10 to the minus 5, whereas the neural network stays roughly at the same value. So I started this with different random numbers. So you now have a 10 to the minus 6 times 10 to the minus 4, whereas the error for the standard numerical algorithm has now been reduced, as expected, since the error goes like delta x to the power of 2 in the approximation to the second derivative. Now we can move on now and look at the calculation. As you can see here, when you look at the graphs, I mean, you barely see any difference. Now we can move on to the solution of differential equations. And one of the first problems which we encounter is that of the diffusion equation in one dimension. And in this case now what we need is a function f which contains the derivatives, either first derivatives, second derivatives, etc. And these are derivatives which then obviously depend on the type of variables which we have. And now we need also to have a trial function which expresses initial conditions and boundary conditions. So the network requirement is now given by a new function which we want to optimize and drive to 0. And again, it's the same type of recipe, except that we are increasing the dimensionality of the problem. So the neural network solver which we have can be kept pretty generic, except that what happens now is that we need to change the derivatives and we need to change slightly the inputs to the cost function, but we would keep the cost function the same, where we simply take the difference between the left-hand side and the right-hand side of the differential equation. So if you look at the diffusion equation, what we would have now would simply be the difference between the left-hand side and the right-hand side. And we would need to plug in the boundary conditions and the initial conditions. So in this case, we have defined x to live between 0 and 1, and we integrate from a final time, t equals 0, from an initial time, t equals 0, to a final time. So we have now, these are the initial conditions, which you see here, the last row. And these are the boundary conditions, because x is defined between 0 and 1. So we are again employing Dirichlet boundary conditions. So we have a g at x equals 0 to 0, and g at x equals 1 to 0. And then when we are setting up the problem here, we are now assuming that this g of x at time t equals 0 is simply given by a sine function. And as expected, when time is becoming large, then we are going to reach an equilibrium situation where the final solution is just going to be a straight line. So we start with a sine function, but then gradually as we evolve over time, then when equilibrium has been reached, all the points will have the same value. And setting up the network here is essentially not that different from what we had before. And I invite you to take a look at it. This is going to take a little bit more time to run, but the setup is basically the same, except that now we have to be a little bit more careful since we are having a differential equations in more than one dimension. But the recipe is just the same as before. So I invite you to take a look at the codes for solving the standard diffusion equation. And we are setting up the trial solutions now. As you can see here, we have a trial solution which encompasses the boundary conditions and the initial conditions. So this H1 now is taking into account the initial conditions, as you can see here. And then we have another part here which takes into account also the boundary conditions. So the first function, h of 1, includes now the initial conditions. And the second term, which you see here, multiplied with the neural network, takes care of the boundary conditions. But we also have to make sure that the initial conditions also obey the boundary conditions. And we need to set up the Jacobian. And the reason for that is that we have derivatives with respect to x and with respect to t. And that's the Jacobian is used because the program must find the derivative of the trial solution with respect to x and t. So this is an additional complication you get when you're setting up a higher dimensional differential equation, which is a partial differential equation. But essentially then the rest follows as before. And the reason why you need the Jacobian is because we have terms like this now. So we are not only dealing with one variable, but we have derivatives with respect to x1, x2, etc. And that's the main complication when you're setting up a neural network for solving a partial differential equation. And if you follow down here, you will also find an example on where we solve the differential equation for the wave equation. So this is given here. So please feel free to look at these equations. And when you solve the wave equation, you have a second order differential equation in both x and t, which also means that you will have two boundary conditions and two initial conditions. So every derivative gives rise to an initial or boundary condition. And in this specific case, we need also to have the Jacobian between, in this specific case, we actually have x and t again. So this is the one-dimensional wave function. So we would again need these Jacobian matrix. And this roughly ends the application of neural networks to the solution of differential equations. And I should say that this is a very, very active research field. And if we go back to where we started, when we started our discussion of differential equations, I invite you to take a look at this exciting research field, which deals with the physics-informed neural networks. And if we go back here, so let's just go back to the beginning of the differential equation part. And there's an article here after all these calculations. So let's just bring it up. So I invite you to take a look at this article here. And if you're on an IP number of the university, you can actually download this scientific article. So if you're interested in this topic, and many of you actually end up doing master thesis project or even PhD projects on physics-informed neural networks. And this is a topic which has become extremely popular, as I mentioned, in the last years. And also it gives very, very precise solutions to high-dimensional and complicated differential equations. And this is where the differential equation solver part is going to stop. Next week, we are going to look at how we can use deep learning to recognize images, which means that we are going to look at the setup of convolutional neural networks. Because one of the drawbacks of the calculations which we are doing with standard neural networks is the fact that we are dealing with what mathematically is called affine transformations. It means that the weight matrix is a dense matrix. We are not skipping any degrees of freedom. The input is then not reduced to a smaller dimensionality. And the matrices, which are multiplied with each other or multiplied with vectors, they keep their full dimensionalities. And we are simply making a transformation or a data set. Now, when we come to convolutional neural networks, we are going to adapt or adopt what is called filters. And these filters serve to reduce the dimensionality of the problem. So if you take an image of a house and you want to build a deep learning method which recognizes houses, then you would keep the information about corners, the roof, number of windows, doors, etc. But you wouldn't keep all the pixels which represent the color of the wall, because the color of the wall is most likely the same all the time. So what you would do then would actually to apply some filter to reduce the dimensionality of the problem. And this is where we will start next week.